In the last lecture, we learned why we need extra mass to explain galactic rotation curves. On the horizontal axis, r is the orbital radius, or the distance from the center of the galaxy. On the vertical axis, v is the orbital speed of a star. And as we proceed outward from the center of the galaxy, each star's orbit has progressively more mass inside it, which would tend to make its orbital speed increase according to this relationship v squared proportional to m over r. However, the stars are much denser near the center of the galaxy, so as we move farther out, the effect of the additional interior mass is overwhelmed by the effect of increasing distance from the galactic center, the little r in this relationship. So this should cause the orbital speed of stars to decrease with increasing radius once we get away from the dense galactic center. But it doesn't. Maybe our measurements of the star's rotational velocities are incorrect. Well, we think we have a pretty good idea of how to do that. The way we figure out the velocity of the star is by measuring light coming from that star. A star's elements absorb particular wavelengths of light, so when we measure the light as a function of wavelength, there are little bites taken out at very specific wavelengths. The positions of these bites shifts to lower wavelength or higher frequency if the star is moving toward us, and it shifts to higher wavelength, lower frequency if the star is moving away from us. This happens for the exact same reason that the frequency of Io's eclipses seems to change depending on whether Jupiter is moving toward or away from us when we measure them. So when the wavelength shifts lower, frequency shifts higher, we say the object is blue shifted, and when the wavelength shifts higher, frequency shifts lower, we say that the object is red shifted, moving away from us. And using techniques we'll learn later, we can calculate the speed relative to Earth by the amount of the shift. Higher shift means larger speed. Okay, so say we're looking at the Andromeda Galaxy. What do we see? Well, that depends on how the galactic disk is oriented relative to our viewpoint on Earth. Here's my galactic disk. If it's just about edge on, we will see the stars on one side of the galaxy moving toward us, while the stars on the other side of the galaxy move away from us. So if this man on the slide were standing in the middle of the galaxy, all of the stars on one side of him would be blue shifted, and all of the stars on the other side of him would be red shifted. Actually, I lied about Andromeda. For Andromeda, we see all the stars moving toward us. They're all blue shifted. Do you remember why? We're on a collision course with Andromeda. In another 7 billion years, the Milky Way and Andromeda will merge, and our two spiral galaxies will become one big elliptical galaxy. But we still see that the stars on one side of the galaxy are moving toward us faster than the stars on the other side of the galaxy, so we can infer that it is spinning as it approaches us. Anyway, if we're right about the speeds, and assuming that we know how to measure r, which is how far away the stars are from the center of the galaxy, then we must be wrong about m. The mass must not be becoming less dense as we move away from the center. Even though the luminous mass that we see is less dense on the outskirts of the galaxy, there must be some more non-luminous mass that we cannot see. Some other evidence that we're wrong about m comes from gravitational lensing. The idea here is that any light that goes past a large mass will change course, and this will cause us to see the object in a different position from the position it's actually in. So in this picture, there's a galaxy on the left and Earth is on the right. But between the galaxy and Earth, there's a large cluster of galaxies. And this galaxy cluster blocks Earth's view of the galaxy in the background. However, because of gravitational lensing, the light from the background galaxy bends around the cluster and reaches Earth after all. From Earth, we see the galaxy's light hitting us from the right and left, but not from straight on, because from the straight on direction, the massive galaxy cluster is in the way. So in our image, we see little parts of a ring. Sometimes, because of the relative positions of the object in the background and the intervening mass in the middle and Earth, the light actually can take longer to go one way than it takes to go the other way. For example, we might see a supernova explosion go off on one side and then see it go off on the other side several years later, the same supernova. So anyway, based on galactic rotation curves and on gravitational lensing, it seems like there must be more mass than we've accounted for. We know it cannot be luminous, but what else could it be? Well, here are some candidates. First, planets. They have mass and they don't give off light. Perfect. But in order for there to be enough planets to account for the rotation curves we measure and the amount of gravitational lensing we observe, there would have to be too many of them. For example, the sun makes up 99.8% of the mass of our solar system. So only 0.2% of our solar system's mass is comets, planets, and asteroids. And most of that 0.2% is Jupiter. So other solar systems would have to have an unlikely number of planets, like 2,000 Jupiters each, for this to be true. Okay, so not planets. How about brown dwarfs? These are much more massive and they don't shine. This is a picture of a brown dwarf on the right of the slide. They're about the size of Jupiter, but they're much more dense and they don't fuse hydrogen. The only problem is that we haven't detected enough of them via gravitational lensing or the infrared light that they emit to be able to say that they might account for all of the missing mass. Okay, next candidate, black holes. They definitely don't emit light, so we've got the dark part covered there. The reason that many researchers have eliminated this candidate is that black holes are usually formed from supernova explosions, which spew heavy elements into space. Heavy elements are elements heavier than hydrogen and helium. We haven't been able to detect as many heavy elements as would have resulted from the formation of the number of black holes that would be needed to account for the observed galactic rotation curves. But maybe the supernovas happened in the early universe, like really early, like time of the Big Bang early. In that case, we wouldn't necessarily detect the heavy elements because around the time of the Big Bang, heavy elements did not exist. In fact, protons and electrons did not exist. The only thing that existed was something called non-baryonic matter, which for our purposes is matter that is not protons or electrons. According to a lecture I attended in summer 2018, some researchers at Lawrence Livermore think that maybe a string of non-baryonic black holes from the Big Bang seeded the early universe with black holes. And this would have resulted in several 10 to 100 solar mass black holes being scattered throughout galaxies, and this might account for the missing mass. They're currently looking for these black holes via gravitational lensing. And if they find them, the accepted theories of dark matter will be turned on their heads. They call what they're looking for MACHOs, massive astrophysical compact halo objects. They've found some. Will they find enough? Maybe. But until they publish it, we'll go with the most widely accepted theory of dark matter. And what is that, you might ask? Well, the leading idea is that dark matter is not MACHOs, but WIMPs, weakly interacting massive particles. What do they weakly interact with? Other matter. Researchers are looking for WIMPs feverishly, spending more and more money and digging bigger and bigger underground tunnels, trying to validate the theory. But no one has found any yet. One final possibility is that we might just have this whole gravity thing wrong. Researchers are currently working on that too, modifying theories of gravity so that galaxies can spin as fast as we observe them to do without making up these fairy tales about some new kind of particle that has mass but doesn't interact with light. So none of the candidates have been completely eliminated. Well, maybe planets have. I don't think anyone thinks it's planets. But we're looking. Where are we looking? In the case of WIMPs, we're looking underground. If WIMPs exist, they're all around us, passing through our bodies at the rate of hundreds per second. But lots of particles are all around us, passing in and out of our bodies. Most of this other stuff would be blocked by, say, several thousand cubic feet of dirt and rock and ice. So scientists are going deep underground to look for WIMPs. We're also looking for dark stars. These are big, puffy stars that don't shine by the light of hydrogen fusion, even though they're mostly made of hydrogen. Instead, they shine in the infrared by dark matter particles annihilating each other. These are WIMP particles annihilating each other, as they would be predicted to do according to a physical theory called supersymmetry. If things went down the way physicists think they did in the early universe, and that is a big if, then there might still be a few dark matter powered stars called WIMP burners near the centers of galaxies. Also, there would be some dark stars in the early universe, which we might be able to detect with the James Webb Space Telescope if they are luminous enough. James Webb is scheduled to launch in 2021. So, in a nutshell, dark matter, if it exists, does not interact with light at all. Really, instead of dark matter, they should have called it transparent matter, though transparent matter wouldn't pack quite the dramatic punch. Physicists made it up to explain why galaxies seem to be rotating as fast as they do. They're making up quite a castle in the sky about it too, with ever more complicated theories of supersymmetry and non-baryonic matter and black holes in the early universe and annihilating particles and dark stars and all sorts of things. Experiments are underway to figure out which, if any of these things, might be what is actually going on. Or maybe it's none of them. Maybe our theories of gravity are just wrong. It wouldn't be the first time. Thank you.